Chapter 21, Transition Metals and Coordination Chemistry. Our outline is transition metals, coordination compounds, crystal field theory, colors and magnetism, and coordination compounds and biology. The coordination compounds and biology section is in the handout. I won't go over it. I'll have you read it on your own. I would say if you don't have a periodic table in front of you, go get one. We will be relying upon looking at a periodic table to determine primarily electron configuration. So go get that periodic table and come back. Here is a periodic table showing most of the elements on the periodic table and a piece of them. If they're gases, it would have to be in a container, or metals. So I thought that could interest you to see what they look like. Some of them, there isn't a piece of them, rather people who were involved in the naming that they ultimately got. Here's another periodic table shown in the middle, and we see the S block shown in gray and purple, the D block shown in gold and expanded above. We see the P block shown in green and blue and, well, two shades of blue. And then we see the F block shown in orange and purple. Transition metals are the D block elements as well as the F block elements. We'll be looking primarily at the D block elements. In fact, primarily at the first row of the D block. And it is the 3D metals. So I have some tables from your book, just interesting information to read over at your leisure. The transition metals are the metals of industry for the most part, and of course chromium, cobalt, and so on. So read over that stuff as it interests you. The next table has alloys containing copper, so brass and bronze. Those are from the brass, the Bronze Age from long ago. Copper and tin primarily are what make up bronze. Brass is also involving copper, primarily just zinc, and it's not as strong but considered more decorative. Sterling silver is primarily silver with a little copper. Gold, 18 karat, 14 karat. So you've heard of course, 24 karat gold, that's pure gold, 100% gold. In 18 karat, it's 75% gold. And in 14 karat, it's 58% gold. So that number, that carat association, has to do with the percent gold in the compound. Next, we have a table of properties of the first row transition metals, and you probably will want to refer to that as you go through the chapter, as you do homework problems on the quiz. Anyway, so that's an important table. A few items I want you to focus on are electron configuration. So with your periodic table in hand, notice that the electron configuration of scandium would be argon, 4s2, and then 3d1. Titanium, the same, argon, 4s2, 3d2. Vanadium, argon, 4s2, 3d3. Chromium, we see 4s1, 3d5. That's not quite what's expected. It turns out it's lower energy for the 4s electron, the second one, to be rather in a 3d atomic orbital. Manganese is what we'd expect, 4s2, 3d5. Iron, 4s2, 3d6. Cobalt, 4s2, 3d7. We're just adding one more electron, of course, one more proton in the nucleus, and cobalt says, is as expected, so is nickel. But then we get to copper and we see 4s1, 3d10. So again, lower energy with that second 4s electron in the 3d atomic orbital. And then zinc, 4s2, 3d10. So that shows a filled, the filled 3d atomic orbitals. The radius, it decreases for the most part as we go from left to right, so the usual trend. We see ionization energies. They increase as the size decreases for the most part. We see first, second, and third ionization energies shown. Next, go to the common oxidation states. So scandium, 3 plus, that means it has lost the 4s electrons as well as its 3d electrons, or 3D electron. Titanium, 2 plus, 3 plus, and 4 plus, those are all common. And in titanium 4 plus, it has lost the 4s as well as the 3D electrons. Vanadium, the highest oxidation state, plus 5, it has also lost the 4s and the 3D electrons. Same with chromium in the 6 plus state, no more s or 4s or 3d electrons. Same with manganese, 7 plus, so no 3d or 4s electrons. But then we get to iron and suddenly we don't have a high oxidation state. We have just 2 plus and 3 plus. Same with cobalt, nickel only 2 plus, copper 1 plus and 2 plus, zinc 2 plus. So as we get more and more electrons, we're also getting more and more protons in the nucleus. So for iron and beyond in that 3D row, the charge of the nucleus is great enough to not make for those high oxidation states. Melting points are high for these metals. They're metals of industry, so they need to have high melting points. Densities are typical for the metals. Electrical conductivity, going down the line there, we see that copper has the highest conductivity. Of the D block elements, it turns out that silver has a higher conductivity, but copper's is very close to it, and that is why copper, which is also readily abundant, is the one that's used in electrical wiring. So next we have the atomic radius versus atomic number. We see the green data is for the 3D row. The blue and the red data are for the 4D and 5D rows. What I want you to notice is the size does, across a row, somewhat steadily decrease. And the 3D are smaller because they have their outermost shell being 3 instead of larger. But notice that for the 4D and 5D, their outermost electrons are at about the same place, even though we have the shell for the 5D being a whole shell greater. But it turns out that the Z effective for the 5D is such that it pulls them, those outermost electrons, in enough to keep them the same size as the elements directly above them in the 4D row. We will come back to that. Here we see ionization energies. They, looking at the first ionization energies, go up as the size gets smaller. Typical. So some general information. The D block contains most of the metals of industry. Copper is found mostly in its natural state and as an ore. Natural state meaning copper without a charge, or that would be copper with a charge, some kind of ionic compound, a mixture of them. It's melted, if it's an ore, it's melted to be made into copper metal. And copper metal, it was found in the long time ago, like in the Bronze Age, so about 3500 BC, it was found that copper can be made harder and therefore more usable with tin, and tin was readily mined as long ago as the Bronze Age. Iron is harder than copper, but it was harder for people to work with a long time ago, which is why the Iron Age didn't begin until around 1500 BC. As we go from the right to the left on the periodic table, we find that they are harder to extract from how they are found in nature as a pure metal. And so iron is found as an ore, so there had to be ways to get it to go from iron 2 plus or iron 3 plus to iron the metal. It took very high heat, that took more sophistication for people to develop that technique. So brass was common from around 900 BC and beyond. So as we move to the left side of the periodic table, we get to titanium. That took very sophisticated technique to get it into titanium metal from its ion, how it's found in nature, electrolysis. It's light, it's used in the aerospace industry. Vanadium is used in catalysts. Platinum we saw is used in catalysts. It's also, as we saw, used in electrodes. Copper, its primary use is for electrical wiring. We have the precious metals in the D blocks, gold, platinum, silver. Of course, we know platinum is common, is enjoyed in jewelry. Metals in general are good conductors, malleable, meaning they can be banged into shape, like made into swords and shields from past times. Metals are ductile, that means they can be made into wires, like for use in electrical wiring. They're lustrous, so they're shiny. Typically, they're silver white. Of those D block ones, copper and gold are exceptions. They have high melting and boiling points. Of course, we know mercury is a liquid at room temperature. So sizes. For the 3D row, they decrease from left to right. There's some exceptions, but in general, that's how it goes. But as we talked about, the 4D and the 5D elements are just about the same size if you go from one element to the one directly below on the periodic table. And that's due to what's called the lanthanide contraction. And this contraction is due to shielding and Z effective. So the electrons are attracted to the nucleus because of the charge of the nucleus, the positive charge of the nucleus. What an electron feels as its attraction to the nucleus is due to the effective charge the nucleus has on the electron. We call that effective charge Z effective. You worked with it in Chem 1. Well, the inner electrons shield the outer electrons from the full impact of the nuclear charge. And the amount that those inner electrons shield the outer electrons has to do with what type of orbitals they're in. Electrons in S orbitals are very shielding. P orbitals, a little less shielding than the S ones. D orbitals, a little less shielding than the p ones. Electrons in F orbitals are the least effective in shielding. So if we compare, for example, osmium and ruthenium, so osmium is directly below ruthenium, it's in the 5D row, ruthenium above in the 4D row. They're about the same size, even though osmium's outermost shell is n equals 5, so one whole number greater than that of ruthenium. Well, looking at the electron configuration of osmium, we have xenon, 6s2, and then we have to go down into the F block at 4f14, and then we're back in the D block, and we have 5d6. That would be osmium's electron configuration. So every time we add one more electron to the atom, we're adding, of course, one more proton in the nucleus. But those 4f electrons, those 14 4f electrons, are not very good shielders. So osmium ends up feeling a much greater Z effective than one would expect given the number of lower electrons in it. But a lot of those lower electrons are these 4F ones, not very good shielders. So the Z effective osmium fields is about the same as the Z effective ruthenium fields, making those two have about the same size. So that's called the lanthanide contraction because osmium would be after the 4F row if we're looking at electron configuration. Densities, well, due to their small size and yet high mass, the 5D elements have very high densities. Of the elements, pure elements on the periodic table, osmium and iridium, those are in the 5D row, they both have the highest densities, a value of about 22.6 grams per ml. Ionization energies are as we expect. They increase across a row due to decreasing sizes. Okay, electron configurations. For atoms, that is, they have no charge. Scandium, we went through argon 4s2, 3d1. We then looked at the others up to chromium, where we would have expected chromium to be argon 4s2, 3d4. But it turns out, as we talked about earlier, chromium is argon 4s1, 3d5. The second 4s electron would rather be in the 3d atomic orbital energy-wise, and that's because 4s electrons shield the outer electrons very well. They shield the nucleus from the 3d electrons. And so what that means is those 3D electrons up there don't feel such a large pull to the nucleus, making them at a bit of a higher energy. But if a second 4s electron jumps up into the 3D orbitals, then there's less 4s shielding, and that makes the 3D electrons a little bit lower in energy and making the atom overall lower in energy. And that's how that happens. The electron configurations for manganese through nickel are as expected, and then copper again has that same situation. The second 4s electron is in the 3D atomic orbitals. That's lower energy for that same reason we talked about. 4s electrons shield tightly enough where if there's enough electrons in the 3D atomic orbitals, it turns out they can feel a better Z effective if that second 4s electron is not in the 4s atomic orbital. Okay, when we have ions of those atoms, that is, electrons have been removed, we have we talked about the maximum possible oxidation states for the first 5 3D elements, so scandium through manganese. Their highest oxidation state corresponds to loss of the 4s electrons as well as the 3D electrons. And then after that, we don't see that. We see that there's fewer electrons lost because of the higher Z effective due to the higher number of protons. What is happening for all those 3D elements when they become ions, they always lose the 4s electrons first. So scandium 3+, well, it's lost all of those 4s and 3D electrons, so it's just got the electron configuration of argon. Titanium 2+, notice that the electrons that go first are those 4s electrons. So we have the electron configuration argon 3d2. Vanadium 2+, it has lost those 4s electrons, so it is argon 3d3. Chromium 3+, it has lost the 4s electrons plus one of the 3D electrons, so its electron configuration is argon 3d3. So, etc. So the bottom line here is the first row 3D metal ions have no 4s electrons. Magnetism, we talk about that a bit in Chem 1. A paramagnetic or a ferromagnetic material is attracted to a magnetic field, and that's due to one or more unpaired electron. Outside of the presence of a magnetic field, so when we take away that magnet, a ferromagnetic material maintains its magnetism, but a paramagnetic material does not. Fe3O4, which is magnetite to a geologist, it is a naturally occurring magnetic material. So that's found in nature. We have some magnetite rocks in our stockroom that you can pick up a iron nail, for example, with. A diamagnetic material is not attracted to a magnetic field. In fact, it turns out to be a tiny bit repelled. And that's because all of its electrons are paired. So if we look at chromium, the metal, so it's got the electron configuration argon 4s1, 3d5. If we look at its electrons in the s and 3d atomic orbitals, we see that they are all unpaired. So if we look at an atom of chromium, and it has a net magnetic moment, a net magnetic dipole moment. And we can symbolize that with a circle for the atom and then an arrow in it, as I've drawn there. So in the picture there, with H field off written below it, I'm showing, let's say, 6 atoms of chromium with their magnetic dipoles just randomly oriented. But they do have magnetic dipoles. They're random. We turn the magnetic field on, or we bring the magnet up to it, depending if we have an electromagnet or a permanent type magnet. Anyway, there's a magnetic field there that causes the moments in the chromium to all line up with the field, and it's attracted to it. We turn the field off or take away the magnet, and the magnetization is becoming random again. In zinc, which is diamagnetic, so we see the electron configuration 4s2, 3d10, we have all paired electrons. And that is to say there's no net magnetic dipole moment, so it would not interact with a magnetic field, at least not much. In a ferromagnetic material, once we expose it to the magnetic field, then the direction can be maintained. So even with the magnetic field off, if we had iron or cobalt or nickel, those are all ferromagnetic materials, they would behave as magnets due to their unpaired electrons and the fact that they can hold on to that orientation without a magnetic field. Okay, now we get into coordination compounds. Those are also called transition metal complexes, or just simply complexes, or maybe complex ions. We'll see as we go on that we use lots of terms for them. They contain a transition metal with ligands, where ligands are molecules or ions with at least one lone electron pair that forms a covalent bond to the metal. It forms a coordinate covalent bond because both electrons of the covalent bond come from the ligand. Okay, so let's read that again. Coordination compounds contain a transition metal with ligands, where ligands are molecules or ions with at least one lone electron pair that forms a coordinate covalent bond with the metal. We can have neutral complexes, neutral compounds, and we could symbolize one of these as MLN, where M is the transition metal and L is the ligand, and the little n represents how many ligands are attached to the transition metal. An example of a neutral complex is NiCO4. So Ni is the transition metal, CO is the ligand, and there's 4 of them. We can also have charged complexes where we have the complex MLN as the cation and then some kind of an anion making it overall neutral. So that the MLN M plus, where the M plus is the charge of that complex, it is the complex ion, cation, and the anion, we could call it the counter ion. It's just what's keeping that overall compound neutral. An example of a charged complex where the complex ion is the cation is CO NH3 6Cl3. So what we have is the complex is CO NH3 6. The NH3 is the ligand. There's 6 of them attached to the cobalt. So that makes up the complex ion. And then Cl, there's 3 of them. Each one is Cl minus. They are just the counter ions. They're indicating that that complex must have an overall 3 plus charge, since 3 Cl minuses are needed to make it neutral. We can also have charged complexes where the complex is an anion. So an example of that we could symbolize in general as cation, MLN. The cation is the counter ion. It could be sodium, potassium, etc. And MLN, M minus, is the complex ion. So an example of this kind of a charged complex where the complex is an anion is Na3FeCN6, where there's 3 Na pluses. They indicate that that complex must have a 3 minus charge overall. We see this, the metal in the complex is iron. The ligand is Cn. It's actually Cn minus, and there's 6 of those. The bond between the counter ion and the complex ion is an ionic bond. The bonds between the metal and the ligands within the complex are the coordinate covalent bonds. Often charged complexes are water-soluble, where usually the complex ion stays intact. So here's an example of a complex that is involving iron as the transition metal, H2O5, so that means there's 5 water ligands, water molecules attached to the iron, and we have a chlorine, a Cl minus associated with it, and also an OH minus associated with it. So let's say that we don't know whether the chlorine is part of the complex or the chlorine is the counter ion. So we have 2 possibilities. FeH2O5Cl in the square brackets, that would imply that's the complex with OH minus as the counter ion, or it could be FeH2O5OH, so that's the complex, and then Cl minus the counter ion. So what we do know again is that the waters are all part of the complex, and of course the iron is too, but whether the chlorine or the hydroxide is, we aren't sure until we do some kind of an experiment. One type of experiment is to dissolve the compound in water. So we have, looking at those reactions, we have if it is FeOH, FeH2O5ClOH, then when we dissolve it in water, the OH being the counter ion, that would be floating around in the water, and then the complex ion involving the chlorine would be floating around intact in water. If, on the other hand, the OH minus is part of the complex and the chloride is the counterion, then when we dissolve that in water, we would have Cl minus floating around. OH minus would be part of the complex. That's an ion also, of course, floating around. So what we would have to do is add something to our dissolved compound that would interact with the OH minus. For example, if it is a counterion, but not with the Cl minus. If it, on the other hand, is the counterion, well, if we use magnesium nitrate, then that will form a solid, which we would visually see if OH minus is the counterion, and not if the Cl minus is the counterion. So depending on our experimental results, we would know what the molecule, this complex looks like. If we get a solid, we would know that the OH minus is on the outside, so our compound would be FeH2O5Cl OH on the outside. If we don't get a solid, then we would know that Cl minus is on the outside, and our compound is the second one, the FeH2O5OH with Cl on the outside. Okay, now we'll get into the ligands more. The ligands can be neutral or charged. The ligands can form only one covalent bond with the metal, and if so, they're called unidentate ligands or monodentate ligands. Some ligands are bidentate ligands. They form two covalent bonds with the metal. They kind of wrap around it. Some form even more than two covalent bonds with the metal, and we often refer to those as polydentate ligands. So here's a table of ligands, common ligands. The common unidentate, that is monodentate ligands, are water, neutral, ammonia, neutral, Cn minus, NO2 minus, SCN minus, OH minus, and then the halogens like Cl minus, Br minus, halide ions. Two common bidentate ligands are oxalate, and where it attaches are on those two singly bonded oxygens. So each one forms a covalent bond with the metal, which is given by that symbol M. It's a big enough molecule that it can kind of wrap around and bond in two spots. Another common one is ethylene diamine, often just symbolized En. So that's also a big one, and it, at its nitrogens, where there's lone pairs, actually one lone pair on each nitrogen, it forms that coordinate covalent bond. We could also say the ligands are acting as Lewis bases with their pair of electrons to donate. Some common polydentate ligands are diethylene triamine, so that's attaching in three spots. It's much bigger, so it can really wrap around. And then a very unusual but rather common polydentate ligand is EDTA, ethylene diamine tetraacetate. Notice that it can attach at 6 spots. So the oxygens, the two on the left in the diagram, they form each coordinate covalent bonds. The two nitrogens in the middle, they each form a coordinate covalent bond with the central metal, and then the two oxygens on the right side. So it's makes for 6 connections to the central metal. It really wraps around it and surrounds the central metal. Sometimes EDTA is used in various liquids because it can grab onto metal ions that would be found in water that's used to make these liquids like sodas and maybe sometimes certain other beverages. And so they can precipitate out the metals like calcium ions. I know that's not a transition metal, but that's a common ion found in water. And this EDTA can be used to precipitate out the ions so that we don't see them and wonder what are those things floating around in my soda. So this These diagrams are showing the metal and the bond that the ligand, like we see NH3, that's a neutral one. It's a monodentate ligand, so it makes just one attachment. And the second one is ethylene diamine, so we see that it is a bidentate ligand. It attaches in 2 spots. Oh, by the way, the oxidation state of the central metal is the charge of the metal. So in this diagram, in these diagrams, it would be N plus. They're always cations, or they're neutral, the transition metals. Here is ethylene diamine surrounding the central metal. So the central metal given by the M, and then we see attachments, there's 6 of them to the metal. The 2 oxygens on the left, the one in kind of the back, the one in the front. We see an oxygen above, we see an oxygen below, so that's 4. And then we see the 2 nitrogens on the right side making up 5 and 6. So really surrounding that metal. The number of bonds formed between the metal and the ligands is the coordination number. Common coordination numbers are 2, 4, and 6. So ethylene diamine, just one ligand would have a coordination number around a metal of 6 if it were the only ligand attached to the metal. So the coordination number is the total number of those covalent bonds to the metal. And again, common numbers are 2, 4, and 6. So we see a table here showing various transition metals and common coordination numbers for them in these complex compounds. So we see 2, 4, 6 repeating quite a bit. The shape, the geometry is linear when the coordination number is 2. We see an example of that with the complex Ag and then 2 NH3s. It overall has a plus charge, as we see in the picture there. And it's a linear molecule, so that's coordination number of 2. By the way, the ligands are neutral, ammonia, and so the overall charge of that complex ion must be just the silver, it must be Ag plus. The shape is either tetrahedral or square planar when the coordination number is 4. So here are those 2 possibilities. So when coordination number is 4, we have either tetrahedral or square planar. For the tetrahedral structure, we have the example of zinc surrounded by 4 ammonias, and it does so in this tetrahedral fashion. So the ammonia is neutral, the overall charge of the complex is 2 plus, so that must mean that the zinc has a 2 plus charge. The electron configuration, as you can see from your periodic table, for zinc is argon 4s2 3d10. So zinc 2 plus has lost those 2 4s electrons, so it is a d10 ion. And we're going to see that it's important to us to know how many d electrons the central metal has as we go on in our chapter. Okay, so some coordination number 4 complexes have the square planar shape. An example of one of those is platinum with 4 waters around it. Waters are neutral, like ammonia is neutral. We see again the overall complex has a 2 plus charge, so that must mean platinum has a 2 plus charge. And what kind of a metal is it? How many d electrons does it have? So platinum has the electron configuration that shows we have in the metal, so before being charged, we have 6s2, and then we have 5d8. Well, it loses those 6s electrons when it becomes 2 plus, so it's simply a d8 ion. Alrighty, so the shape is octahedral when the coordination number is 6. And so there we have coordination number 6, octahedral. So we have the metal in the middle with the ligands at the corners of the octahedron. An example of that is nickel with 6 waters around it. And in this case, it's got an overall 2+ charge. So the nickel, being that water is neutral, has the 2+ charge. And if you look on a periodic table, you will find that when nickel loses those 2 4s electrons, there are 8 3d electrons left over. So it's a D8 ion. We are skipping the nomenclature and the isomer sections. So when you read over the chapter, you can know that you won't be tested on those 2 sections. Okay, our next topic is the crystal field theory, where we can understand colors and magnetism. So we will talk about the octahedral complexes, then we will talk about tetrahedral complexes, then square planar, and then linear. So starting off, octahedral complexes. So let's take this complex, K3TiCN6, and dissolve it in water. So the potassium counter ions split away and we have the titanium complex. So TiCN6, 3-. We know it's a 3- charge because the total neutral compound is written with 3 K pluses, so we know that the complex is 3-. The CN- is a monodentate ligand. There's 6 of them, no other ligands, so we know that the coordination number is 6. So we know, well, it's octahedral. The oxidation number, or charge or state of titanium ion, must be 3+ because that overall complex is 3-. There are 6 CN-, so that means the titanium must be 3+. Looking at the periodic table, before the 3+, when we have titanium, the metal, it's electron configuration argon 4s2 3d2. So we take away 3 electrons and we're left with just a D1 ion. So there is a picture of it. It's the carbon that has the lone pair of electrons to make for the coordinate covalent bond with the titanium 3+. The ligands are attracted to the plus ion. So titanium has a positive charge, so the ligands with their electrons and even their charge, they're attracted to that positive ion. This attraction lowers the energy as the molecule forms and is a major factor in the stability of complexes. It explains why they form. The titanium's d electron interacts differently with the ligands depending on which of the 5 d orbitals it occupies. Okay, so what we have, and we will go to our next page for pictures, what we have are, on the titanium, its 3d electron is in the 3d atomic orbitals. And in this view here, we see that there are the 5d atomic orbitals with their shapes shown in the purple. We have the dz squared atomic orbital. It has that shape. Notice it's along the z-axis. We have the dx squared minus y squared. So that shape, those lobes of that d atomic orbital are pointed toward the corners of the octahedron. And then we have the 3 others that are the dxy, the dyz, and the dxz. Now those are the 3D, the shapes of the d atomic orbitals that are on the titanium, and it's got an electron that can move about in these d atomic orbitals. So that's the metal itself and its 3D atomic orbital shapes. Now, when the ligands come into the metal, because we have a coordination number of 6, those ligands are coming in to the 6 points on the octahedron. So they're coming in above, at the top, at the bottom, and then at the same plane of the central metal as we see in that diagram there, to the left, to the right, in the back, in the front. Now, the ligands, as they come in with their electron pair, they're going to affect the d atomic orbitals differently because of the different locations of the d atomic orbitals. They're going to affect the dz squared atomic orbital a lot. They're going to affect the dx squared minus y squared atomic orbital a lot because they're coming in right where those have lobes. And what that does is it takes the, prior to this complex forming, the diatomic orbitals, which are all degenerate, they all have equal energy, it takes them and it splits them. It causes the dz squared, dx squared minus y squared orbitals to move to a higher energy because they are, remember, they have electrons in them, and as the ligands come in with their electrons, they're, you might say, more repelled. The electron doesn't want to be in those as much. They move to a higher energy. These three, the dxy, the dyz, the dxc, those ones are less affected by the incoming electrons on the ligands. So they're not moved to as high an energy position as the upper two. The upper two orbitals together are called the EG ones. The lower three orbitals together are called the T2G orbitals. Okay, so going back now to this page here, we have that, what I was saying before, two d orbitals, the dz squared minus dx squared minus y squared, they're directed toward those negative ligands. Their energy goes up the most, and they are together at the same energy, symbolize the EG orbitals. The other three orbitals, the dxy, the dyz, and the dxc, are between the negative ligands. Their energy goes up the least. They are symbolized the T2G orbitals. So what we get is a energy level diagram that is shown here. So initially in the atom, in the titanium, before the complex is formed with its 1 3D electron, so it's already actually ionized, it's the Ti3+. So as the complex forms, those degenerate 3D atomic orbitals, they split, and we have the EG ones at a higher energy than the T2G ones. This energy splitting is symbolized delta, and we have the electron going into the lower energy, one of the lower energy atomic orbitals. It's in one of the T2G orbitals. So the electron configuration, we would say, is T2G1, and it is paramagnetic because it has one unpaired electron. Okay, that now sets us up to be able to talk about colors. So for most complexes, if there's, okay, for most complexes, they can absorb light in the visible spectrum because the gap between the T2G orbitals and the DEG orbitals is just right in the visible spectrum. It's not a big gap, which would put it in the UV part of the spectrum. It's not a very tiny gap, which would put it in the infrared part of the spectrum. It's just got the right size in most of these complexes to be in the visible spectrum. That means that the electron is easily moved up and is just moved up by visible light. If we did an absorbance versus wavelength study of a complex, we would find that it absorbs light most likely in the visible spectrum. It absorbs the most at the where it peaks. That would be the wavelength that would describe basically the gap, and then it drops back down. This absorbed light is removed from the white light spectrum, and the complex is not white. It has a color like blue or green or red. The color is usually the complement of the absorbed light on the color wheel. Alrighty, so here we have a color wheel, and what we have is if the complex appears green, it probably is absorbing in the red region. Notice that the color wheel, let's see, I started Roy G. Biv, going from low energy to high energy. So we have red, and then going counterclockwise, orange, a little higher in energy, yellow, a little higher, green, higher yet, blue, and then we get into violet, which is at the highest energy end of the visible spectrum. The visible spectrum runs from 700 nanometers, that's the red end, to 400 nanometers, that's the violet end. So if a complex is green, it probably absorbs in the red region. If it is orange, it probably absorbs in the blue region. If purple, probably absorbs in the yellow region. And here is a spectrum shown where we have approximate wavelengths for those different colors. And then here is a table showing that if it's absorbing, for example, go down to the bottom, in the red region, it probably appears green. If it's absorbing in the orange region, it probably appears blue. Colored solutions. Copper 2+ solutions also often appear blue with a predicted absorbance in the orange range. Fe 3+ solutions often appear orange with predicted absorbance in the blue region. Nickel 2+ solutions often appear yellow with predicted absorbance in the violet range, and so on. Alrighty, so you recall from when you worked with light that the energy of a photon is equal to h nu, where nu is the frequency, or the energy of the photon is equal to hc over lambda, where lambda is the wavelength of the photon. Now, it's photons of light that are being absorbed, causing the electron to move from the lower energy T2G state to the higher energy EG state. So the energy of the photon, hc over lambda, is equal to that energy gap, delta. So we have delta, which is the electron transitional energy gap, equals hc over lambda. H is Planck's constant, and c is the speed of light. Wavelength is in the denominator, so when it is small, that is, we have a short wavelength, we have a big delta. So as the wavelength of light absorbed decreases, the gap would be increasing as we go from complex to complex. So for this titanium compound we've been working with, TiCN63-, by an experiment, it is known that it absorbs light at 420 nanometers. So it is absorbing in the violet range. Calculate the delta. What is the color of the complex? Alrighty, so titanium 3+ has that one d electron, so it's a d1 ion. So we have that delta equals hc over lambda. H is 6.626 times 10 to the minus 34 joules seconds. C is 2.998 times 10 to the 8th meters per second. And now we have to convert the wavelength into meters to make units work out. So we have 420 times 10 to the minus 9 meter, because nano is 10 to the minus 9. When we do the division, multiplication, we get delta equals 4.7 times 10 to the minus 19 joules. That would be joules per complex. And if we converted from joules to kilojoules and from complexes to moles of complexes, we get that delta is 280 kilojoules per mole. The complex, by the way, since it is absorbing in the violet region, we would predict it to be yellow. Here is, in that first row of this table, we have the energy splitting diagram there. The ligand, if in our complex, if it's Cn minus, we were told and worked with the wavelength of absorbed light is 420. We calculated the delta to be 280 kilojoules per mole, and we predicted it to be yellow. Now, if instead of this titanium 3 plus with 6 Cn minuses, if we have 6 waters and did the experiment to measure the peak absorbance, we would find it's 520 nanometers. From that, we would calculate delta to be 230 kilojoules per mole. So verify that yourself, that you would get that number. Given where it absorbs light, if we look back at the spectrum, we might predict that it's absorbing in the green region, so we would guess it would appear red. If, on the other hand, we have that titanium 3 plus with 6 Cl minus ligands around it and measured the peak absorbance, we would find it 610 nanometers. From that, we would calculate delta to be 190 kilojoules per mole. So once again, verify that yourself. 610 is around the yellow region, so we would predict blue to be the color of light absorbed. Now notice that as we go from Cn minus down to Cl minus for the ligands, we see the delta, the energy gap, getting smaller. And I tried to show that in the pictures in that first column. Cn minus, big gap. Cl minus, little gap. So the Eg orbitals are pretty close to the T2G ones. It turns out that for most complexes, the ligands follow this trend independently of the metal that they're attached to. That is, Cn minus, when that's there, or Co, the gap, the delta tends to be very large. When we have the halide ions, Cl minus, F minus, Br minus, I minus, we have a small delta. And that works for very commonly for these complexes. So what we have is what we call a spectrochemical series, where at the top we have the ligands that make for the biggest delta. Notice Cn minus up there, CO. Below that we have NO2 minus. Below that En, that's that bidentate ligand. Then we have ammonia, then we have water. Then we have the C2N2, 2 minus oxalate. Then we have OH minus. Now we're getting to pretty small deltas with those halide ions. When we have a big delta, when we have a ligand up at the top of this spectrochemical series, we call that a strong field ligand, makes for a big gap. When we have a small delta, we call that a weak field ligand. Okay, the last column of that table has us working with a central metal that has the electron configuration D6. If we have it hooked up to a ligand where the gap is big, then when we go to put the electrons in the atomic orbitals, we would put the first 3 in separate T2G atomic orbitals, and then we would pair the other 3 electrons in those same orbitals. And so we would end up with the electron configuration being T2G6, and that would be a diamagnetic compound. When we have a small gap, then we put those 6 electrons in, putting 3 in the T2G ones, and then putting 2 in the EG ones, and then we would start pairing. So its electron configuration would be T2G4EG2, and due to those unpaired electrons, we would have it be paramagnetic. So what we have is a lot more spin in the case of the weak field ligand, and we can often call those types of ligands high spin ligands. In the upper case, where we have a strong field ligand, we have not as much spin. We call those low spin ligands. So here is, once again, that spectrochemical series. And then we have the color wheel. And we're going to apply that looking at some of the data in this absorbance versus wavelength graph. So what we have is a cobalt compound where it has some of the ligands. Let's say we have 5 ammonias and we have 1 other ligand. If that other ligand is NH3, then we get that yellow absorbance curve. Notice it's peaking at about 470 nanometers. If we have water as that last ligand, then we have the red peak that is we have the red absorbance curve. Its peak is just to the right, to the lower energy, the longer wavelength side of the yellow one. Well, on our spectrochemical series, water is lower than ammonia. The last absorbance curve to look at is the blue one that has Cl- as a ligand. Notice it peaks at the longest wavelength, that is to say the lowest energy. And Cl- is on our spectrochemical series here, down below ammonia and down below water. Okay, next we have zinc H2O6 2+ and zinc CN6 4-. These are colorless. Why? Okay, so the zinc in both of these must be zinc 2+, so verify that yourself. And if you look at the periodic table, you see the electron configuration for zinc is argon, 4s2, 3d10. That would be for zinc, the metal. If we take away 2 electrons, then we end up with argon, 3d10. So we have a d10 metal. So regardless of whether we have water or CN or CN- or any other ligand on the zinc 2+, we end up with the atomic orbitals filled. So no matter how we have to do it, whether we pair first or not, they're going to be filled. The orbitals are full. It is colorless and diamagnetic, not due to delta being outside of the 400 to 700 nanometer range, rather due to d orbitals being full. Electrons might be able to move to a higher energy level if light is absorbed, like maybe one of those EG electrons could move up, but the absorbed light would not be in the visible range. That is to say, it's only when electrons are moved between the T2G and the EG orbitals that happens to affect visible light. To move them higher, probably it would take UV light or possibly IR, but it would not be in the visible spectrum. And that's why zinc compounds are colorless. So here are solutions of complexes. And in the just a reminder of what I was saying. Metal ions that contain partially filled D subshells usually formed color usually form colored complex ions. Ions with empty d subshell, so D0, or filled d subshells, so D10, usually form colorless complexes. So in this figure, from left to right, we have scandium 3+, so that's a D0, colorless. No electrons to be moving in that, in the between the T2G and the EG. Next we have chromium 3+, that's a D3 one, so we can have movement, it has color. Next we have cobalt 2+, D7, electrons can move, it has color. Then we have nickel 2+, D8, again color, electrons can move. Next we have copper 2+, so that's a D9, electrons can move. And then finally we have the zinc 2+, which is a D10 ion, so electrons cannot move in that between T2G and EG. Okay, so that's our introduction to octahedral complexes. Now we're going to apply the same kind of stuff to tetrahedral complexes, which have the coordination number of 4. So we see those 5 d orbitals shown in purple again, and we also see them superimposed on the tetrahedral complex. So that's in this diagram B. And it's hard to see as clearly as we could with the octahedral one, but the orbitals that are most affected are those in the lower 3 ones. The orbitals that are most affected are the dxy, the dxc, and the dyz. So it's those that are going to be moved to a higher energy level. So if we look at the 3D atomic orbitals being degenerate, and then the complex ion ligands coming in, causing the splitting, we have this splitting here. Those upper 3 now in the tetrahedral complex, we call them T2, and the lower 2 we call simply E. And actually those T2 orbitals are a little bit less affected than the EG orbitals of the octahedral complex. So the deltas in all tetrahedral complexes are relatively small. They're in the visible range, but they're relatively small. The tetrahedral delta, we could call for the moment delta sub T, that's about half or 4/9 of the typical octahedral delta. So we see by comparison, when we have octahedral, we have a big gap, tetrahedral, a small gap. So octahedral, our energy level diagram is 3 low, 2 high. Tetrahedral is 2 low and 3 high. Looks a little like a T if you use your imagination. Because the tetrahedral delta is small, it turns out that when we place electrons within it, we always would put 2 in the lower ones, and then the third one would go into the T2 level. And we would put the 5th one in the 4th one in the T2, the 5th one in the T2, and then we would go back to the E ones with pairing. So there are no ligands that produce the strong field case in tetrahedral complexes. All right, so that's tetrahedral. Now we move into square planar, which also has a coordination number of 4. It turns out that most D8 coordination number 4 complexes are square planar. All right, so there's the square planar shape. And then we have in orange the shape of d orbitals just once again. And you can see by comparison of the d orbital shapes with the complex shape, you can hopefully determine that the ones that are most affected are going to be the dx squared minus y squared. That's going to be the ultra most affected. So that's going to be at the highest energy position. And then the next most affected one is going to be the DXY one, because that also has lobes right there in that same plane. And the next most affected is the DZ squared one, because it does have that one portion, that circular portion that's in the XY plane. And then the last two with lobes on other planes, those are the least affected. Okay, so that's the energy level diagram for the square planar. And when using that, electrons usually pair before going to a higher energy orbital. So let's say that we had 5 electrons. We would fill the lower two. We would have 2 electrons in each of those lower 2 orbitals before going into the DZ squared orbital. Electrons pair before going to a higher energy state. Okay, so here's a problem. Let's say that we have FeCl4 2-. We know that it's got a coordination number of 4 because we know that Cl- is a monodentate ligand. There's 4 of them. Coordination number is 4. And we're wondering, is it tetrahedral or is it square planar? So what we know from experiment is that it is paramagnetic. We would determine that the Fe is Fe2+. Looking at the periodic table, we would see that it's a D6 ion. So the two possibilities are the square planar, that's the one on the left, and the tetrahedral, that's the energy level diagram on the right. So putting electrons in the square planar one, we would put 1, 2 in the 3, 4 in the bottom, the lowest energy ones, before going up to the upper one to put the last 2 electrons in. So that makes it diamagnetic. But looking at tetrahedral, we would spread the electrons out as I've shown, and yes, indeed, it's paramagnetic. So we would determine from that that the geometry is tetrahedral. Our last shape is linear. Coordination number is 4, and there we have a ligand above, a ligand below the central metal. So we compare that shape to the shapes of the d orbitals, and we see that the one most affected would be that dz squared, so that's at the highest energy. And then we see that the other ones that have electron density along the z plane would be the next most affected. That would be the dxz, the dyz orbitals, and then the least affected would be the dx squared minus y squared and the dxy, because they have no big portion along the z plane. In most linear complexes, the electron configuration of the metals are D10. An example is this AgNH3 2+. Thus, the orbitals are totally full, actually having 10 electrons. So whether or not electrons pair before going to the next higher energy orbital. Okay, our last section is coordination compounds and biology. I know a number of you are biology majors, so definitely take a look at that. It's interesting. Take a look at it at your leisure. Alrighty, so be sure to look over your handout notes carefully, run through all the problems, the examples that we've talked about, verify that you could do those calculations and predict colors and so on yourself. Read the chapter carefully in your textbook, do the assigned homework problems, and be sure to take the quiz for this chapter when it's open.